Welcome. So welcome, Kerem, Abdullah, Kareem. Uh,
Hello.
you can hear me, right?
Yeah, yeah, I can hear you.
Okay. So as we talked last time, today, inshallah, we will do geometry. We will start doing geometry. In fact, I would like to begin with solving your geometry problem from yesterday's test. I actually haven't seen your papers. Did you try to solve it, or did you solve it? Can you tell me? But I will grade. I think Tahsin is gonna send me the papers and I'm gonna grade.
I didn't solve.
Okay. How about others? Kerem and Abdullah.
I didn't solve it too.
Okay. So this gives me a pretty good sense of your level in geometry, and as you indicated, guys, let me tell you that for someone who is equally trained in all four areas, that was the easiest problem in the test. But it seems okay, Kerem got lost, but hopefully he can come. So Kerim, you had said that geometry is difficult last time. I think this is only a subjective statement, which is a consequence of the lack of emphasis in training so far on geometry. So I believe, inshallah, I'm strongly confident that with sufficient geometry training, you will not feel like that. There is no reason you should be afraid of geometry. It is very, in fact, especially the easy problems in geometry are uh, like with after some level of experience, they almost become straightforward compared to the other areas. And there is even some objective measure of this. You may have heard that Google AI company DeepMind has some AI models, deep neural deep learning models, yeah, uh, that whose names are Alpha Proof and Alpha Geometry. Have you heard of this news that Alpha Proof solved the number theory and the algebra problems from last year's IMO? The three
I
problems.
heard that there was some AI that solved the geometry problem.
Yeah, yeah.
They didn't.
So Alpha Geometry, both of them are Google products. The names are Alpha Geometry. They also have other versions of the same AI called AlphaFold, for example. I think for protein folding in molecular biology, stuff like this. Uh, I don't know what is common to them, but uh, so Alpha Geometry solved the geometry problem in seconds, in 3 seconds. But Alpha Proof solved the number theory and the algebra problems in a day or 2 days or something like this. And right now they cannot solve the combinatorics problems. So this even shows that the basic level of geometry in IMO problem 1, problem 4 level, and even problem 2, problem 5 level. It's really a matter of experience. Once you learn it, uh, of course, you don't solve the problem in 3 seconds, but you almost solve all. Once you really get to learn it, you almost solve all of the number 1 and number 4 problems in 40 minutes, in 1 hour. something is within reach. Now, let's say, realistically speaking, for you, within a training of 3 weeks, it is still very possible that you learn most of the basic structure of geometry. So there is some basic structure of geometry that you learn, and the learning happens at 2 levels, essentially. One is to learn the necessary theorems and the relationships between them. And the second level is really internalizing through exercises, solving a lot of exercises and internalizing that knowledge. That is maybe the process to take time, but learning the necessary theorems and the relationships between them is just a matter of 2 or 3 training sessions. So let's hope that we will really, inshallah, get somewhere. So the key for us to in the beginning is to not be afraid of geometry. Okay. So the problem that you didn't solve yesterday is one of those straightforward, easy problems. So with enough training, it's a problem that you cannot miss. Okay, it's really easier than the other problems that you already are able to solve. You are able to solve more difficult problems in number theory and combinatorics. So once with enough training, this is the kind of problem you really cannot afford to miss. It's just so you must solve it, kind of thing. But as I said, if you have not solved, there could be 2 reasons. Either you don't know the necessary theorems, or you just have learned the theorems, but you have never applied them yourselves. So which one is the case? Do you think you also have lack of knowledge in theorems? Probably, or you just know the theorems but never applied them and never seen how to apply them. Which one is the case?
For me, I think both, but mostly using the theorems.
Yeah, so the basic things, like, for example, like angle chasing things, for example, or power of a point with respect to a circle.
Yeah, I know these.
Yeah. Karim and Kerem, how about you?
Yeah, I know these two.
Me too.
So you know power of a point with respect to a circle.
Yeah.
Okay. Okay, let's begin with then solving this problem. And then after solving this, I will give you a lecture style introduction to these subjects. Even though you know them, it is, I think, worth to go through it, at once in some sort of condensed structure of knowledge. But before giving you that lecture, since you already have enough background knowledge, I can immediately tell you the solution of yesterday's problem. Okay. So I think you can remember the problem, right? It was triangle ABC. There's angle bisector. I typically use this color coding. I mean, not when I work on paper, because I have only one color of a pencil, but when I teach online or even physically on the board, we usually have colors available. So I like to use them in geometry. So there are these other angle bisectors, and we know that they are concurrent, right? So always, you also know this. This is the in-center of the triangle. So the other points that were defined was the perpendicular bisector of AD intersecting these blue lines. So first of all, were you all able to draw the picture correctly, or no? No. So this is the first step. This is why I'm asking.
Yeah.
So you drew this picture, but you just didn't know how to prove that these points are on a circle. right? So the approach is this, the way we try to solve these problems is try to understand the points, try to understand the configuration. The base of the configuration here is the triangle. So it's an arbitrary triangle. An arbitrary triangle is given with its incenter. This is a unique specific point of the triangle. And we have AI, BI, CI, which are the angle bisectors. So this is the standard setup. Now on the standard setup, the interesting points in the problem are M and N. So we have to understand these points. So I always say this as a mantra, as a sort of motto in my geometry trainings. Geometry, Olympiad geometry, is about shapes. What is a shape? Shapes are structures that consist of points, lines, and circles. Okay, and the relationships between them. So this is my geometry philosophy. Okay, my philosophy to geometry for plane geometry, Euclidean plane geometry. I mean, as far as Olympiads are concerned, shape is an abstract notion. It's not the same as picture, figure. Well, I use the word picture a lot, which is what we draw. And when I say shape or configuration, this is the more abstract concept. And this concept, this is like a set. You can think of it as a set, but with more structure. So there are points, there are lines, and there are circles, and there are relations between them. What is a relation? What I mean is, so A is a point, and AB is a line. And the relation is that A is on the line AB. So the line AB goes through the point AB. Goes through the point A and goes through the point B. So it's it's not just just points and lines. So this is not what we do in geometry, of course. What we do is we have points, we have lines, we have circles, but there are relations. Like circles go through points. Sometimes there are 3 points on a line and 4 points on a circle. These are relations. And circles could be tangent to each other. Circles could be tangent to lines. Lines could be parallel to each other, etc. Okay, these are the kinds of relations. So let me write this as... Okay, I'll just say this verbally, but hopefully I'll write it when I start lecturing. So this is my encompassing philosophy for Olympiad geometry. We have shapes, and what we are trying to do when solving a problem is to understand the shape, which means understand the relations precisely. So understand the objects with respect to the other objects. So here A, B, C, D, I, these points are the primitive, basic, at the zero level objects. So there is not much to understand because this is the completely standard picture. When you don't have M and N in the picture, there is really nothing interesting. I mean, everything is obvious. There's not much. All the relations are transparent. Now, M and N are defined interestingly. So these are 2 points. What are the characterizations of these points? M is on the line CI, and it is also on the line which is on the green line, which is perpendicular to AD at the midpoint of AD. So this is the midpoint of AD. So this green line is the important line that we sort of need to understand. And the points on the green line, what is special about them? And when it comes to M, especially being on the green line and on the angle bisector, what properties follow from this? What do we learn from this about the point M? So what happens in geometry is typically that many things are congruent to each other, logically congruent to each other. Okay, welcome, Hassan. So many things are logically congruent to each other. So, Hassan, to give you a heads up, we started solving the geometry problem from yesterday, but we haven't said anything yet. We just set up the problem. So we are discussing how to begin the solution. And I said the first important thing I said is really when you look at this, the problem catches you at understanding the points M and N. And this is why this problem is simple, because there are only 2 points that you should understand and they are symmetric. So there is really one thing you need to understand. In more difficult geometry problems, there are points that you need to understand that are also defined in terms of some other points which are also defined in complicated manners. So there are sort of 3 layers sometimes of points that you need to understand. And sometimes there are objects that are defined in a way that is not very easy to handle. Here, the definition is just an intersection of the things. So this really requires a bit of a knowledge. What happens when you sort of intersect a perpendicular bisector with an angle bisector like this? So you have to focus on this part of the configuration. Do you see how this philosophy gets me to start thinking? Focus on M. M is defined in terms of some green line and some blue line, which are, the green line is the perpendicular bisector of something, AD. This is the important thing. Perpendicular bisector. Okay. And this blue line is coming from some, the blue line is an angle bisector. So it's coming from some point C, but it is the angle bisector of ACD. Okay, we see something very important here. Some simplification. We didn't need the entire picture to define M. We only need part of the picture, which makes it even easier to understand what it is. All right. Now, what is the most natural task? To redraw this picture in a way and try to continue thinking about it. How would you redraw this and possibly rename it independently of the problem? In order to understand this, you can give names. You can give the names of the. You can change the names of the vertices so that it can be one of the standard pictures that you know. Then you can understand. You can say, "Aha, M is this point," etc. So this is the moment I want to give you 2 minutes, or maybe even up to 5 minutes, if you can do something. Can you sort of redraw this and rename this? Or can you verbally describe this? So this, or can you try to quickly give a summary of what I have done so far? Very short summary. Can someone try to do that? Because then next I'm gonna say something else.
Okay, so we drew a sketch of the problem setup. Then we sort of slightly analyze it to see what's symmetric, what's important, what do we need to understand?
Exactly.
And then we took a specific uh, specific setup within the setup and try to understand it as well.
Yeah, great. So here you conceptualize the word setup basically. So it's I really like it. So you have the word setup in your mind in relation to geometry. So really, geometry problems have setups and sub-setups, as you said, setup within the setup. This is what I wanted to describe using the word shape or configuration. What is a setup? What's the shape? What's the configuration? Something which consists of points, lines, possibly circles, and relations between them. For example, equality of segments and perpendicularity, these are relations. And equality of angles, etc. These are relations. So this is some setup, some shape, the abstract thing. And also you use the word sketch. Sketch is the picture, which is what we draw. We can draw the same abstract shape in different pictures. For example, we can turn this around and draw the triangles differently, etc. And there are even more sophisticated ways of drawing different pictures of the same abstract shape. I will maybe we can get to examples of those later on. But this is why it is important to understand the distinction between setup and sketch, which is what I say shape and picture. Shape is the abstract notion, which is the points, lines, and relations, and picture is what we draw. And pictures are very important because it allows us to see. It allows us to interact with the problem through our eyes, and then we can start thinking. So this is also why it's important to draw different pictures, to draw the pictures differently. Flip them around and start drawing. So this is really like how you warm up to geometry things. You take it in your hands and you turn it around. And third notion is, in addition to setup and sketch, in addition to shape and picture, the third notion is story, narrative. Every problem also comes with a narrative, because when you read the problem, you don't see any picture, you don't, right? How do they tell you the problem? They tell you the problem in words. They say there is a triangle, there are angle bisectors and intersections, everything is in words. Now, narrative is this. This is the story. It has an order. The story has an order. It begins with some points, and then some other points and lines come, some other circles come, and they come on top of each other in a particular order in the story. But sometimes, not sometimes, many times, in fact, the same shape, the final shape. So this story constructs a shape, step by step, constructs a shape. And then we understand the shape and draw it in a picture. But the same shape many times can be constructed differently, in a different order. You can start with different points and then define the other points in terms of these. You can flip the order of the narrative. You can tell a totally different story and describe the same shape. This is also possible. So shape is always one, okay? So let me write this as on the next page already. So main philosophy for all Euclidean plane geometry. Well, yeah, Olympiad geometry, let's say. Olympiad geometry. So the main notion is the notion of shape or setup or configuration, whatever you can say. So these are equivalent things, okay? So there is this notion. This comes from story. You can call story a narrative, or maybe you can say different words. So the thing is, it can come from many different stories. And this gives pictures. And can give different pictures also. Picture, sketch, whatever you want to call it. Okay, there are three types of objects. The main object, and there is the other objects. Many different stories. Okay, many different stories for the same shape. For bigger shapes especially. For this one, there is not really much story you can say. But for bigger shapes especially, sometimes different pictures for the same shape. Pictures allow us to understand the shapes through our eyes. Pictures are important. And stories usually give us one direction, sometimes give us prejudice. When we don't see the alternative narratives, our minds are sort of stuck in one direction. It's like in real life, like when they tell you a narrative, when there is a conflict between people, when they tell you one narrative, you need to learn the other narratives also. So it's like to understand the shapes, you need to learn the various narratives. So this was good summary, Abdullah. So what I want to now do to understand this, as you said, and either I need to draw different pictures, or I need to just, okay, let me just come up with a narrative for this one. Okay, this is also one way of understanding. Let someone just give me a narrative for this shape. Describe this shape in words as if this is the entire shape, without talking about the rest. Okay.
We have a triangle ADC,
Yes.
and we construct the angle bisector of angle C and the perpendicular bisector of AD, and they intersect in a point M.
So let ACD be a triangle. Okay, can you say it again? We do the angle bisector of vertex C
Of angle C, yeah,
and
the perpendicular bisector
yeah,
of side AD.
yeah. So M is the intersection of the angle bisector of vertex C and the perpendicular bisector of edge AD. Great. So then in order to even better understand this, okay, then this seems like a very standard construction for a triangle, right? Basically, you just have a triangle and you have angle bisector from one vertex and perpendicular bisector from the opposite edge. So to really understand this in generality, the nice way to draw this picture and rename the vertices, I would call the triangle ABC to understand what is going on in this shape, this abstract shape. In generality, I would try to draw the most standard picture with the most standard names, and I would take the angle bisector from here. So basically this A is, so renaming, C becomes A, and other A and D become B and C, right? Now I am telling you, this is a very, very standard picture. If you have not had enough training in geometry, you may not know this. But anyone who has had some training in geometry knows this immediately. This is why, geometry is, in fact, not difficult, but it is just knowing these basic things. And it doesn't, these basic things are not too many, by the way. Knowing about all of these basic configurations just takes, I would say, 3 training sessions. 3 training sessions. You learn about all the basic configurations. And this is one of the configurations. Does any one of you know about this? The properties of this
Yeah,
one?
yeah,
Okay,
I'm here.
yeah,
This point will lie in the circumcircle of ABC.
yeah. Good. Okay, you already know this. How about others? Did you know it?
Not immediately, no.
Yeah.
Oh,
Okay.
oh yeah, from the eccentric form. But I didn't
Yeah.
figure it out while I was trying to
Yeah. So
solve
this is something, for example, one of the things you should just immediately know, right? I'm telling you this with 100% confidence. Uh, I will inshallah tell. So when I do geometry training, my standard curriculum in Turkish Olympiad camps was, I had one training on standard knowledge of the circle and one training on the standard knowledge of the triangle. Okay, it's 3 hours on the circle, 3 hours on the triangle, and in that 3 hours I give whatever all the basic configurations there are, and this is one of them. So what is given in that 3 hours is absolutely necessary knowledge. And there are extra, there is say extra piece of knowledge that you can always learn. For example, you can have say 1 hour on quadrilaterals, etc., and those are also useful. But this basic knowledge of the circle and basic knowledge of the triangle is absolutely necessary, and this is a knowledge of the triangle. So I'll write this as recall. Maybe I can write this on the next page, or even further page. So this basic triangle configuration is this. You have the triangle and consider its circumcircle, okay? Bisectors, angle bisectors, go through the midpoints of the opposite arcs, right? So when you talk about angle bisectors of A, you talk about midpoints of the arcs BC. In fact, what is even a more complete picture is to consider both arcs BC. And in fact, when you even really further understand geometry, you see that the arc is not really about it's not really about having 2 different arcs, but this is just sort of natural two midpoints. Anyway, so there is a midpoint here and there's a midpoint here, and with no distinction between them in terms of their properties. So there is some really interesting things here that I haven't seen mentioned in Olympiad geometry books. I also have not written it, but I have just verbally taught about it many times to my students. There is connections to Galois theory. Some of you might be interested in abstract algebra, maybe now, maybe later, I don't know. Because of those reasons, that there is actually no difference between internal bisector and external bisector. Hopefully, I'll get to tell you about these things as well. So these are the two bisectors.
Yeah, we know the center lemma from
Yeah. So,
yeah.
but together with the circle, this forms this nice picture. So these are these are the mid points. They are opposite to each other. So this is the perpendicular bisector of BC. This is a diameter of the circle. Perpendicular bisector of a chord is always a diameter, right?
Yeah.
You know, so yeah, when you have a chord and when you take perpendicular bisector, that has to be a diameter. It's symmetric. Also, the angle bisectors are perpendicular to each other. That's also something necessary. Because if total angle is 180, you take half of both of them, that's 90. So this 90 degrees also shows that there's a diameter. And since these are midpoints of the opposite arcs, they are opposite to each other in the circle. So they have to form a diameter. So this is the configuration, I mean, to take all of it together. Now, when you draw all of this together from the other edges as well, so there are these two. Then the other two are these. Yeah, somehow my picture is bad because my circle was not good. But I will try to fix the picture. Yeah, this is the midpoint. And this is this midpoint. So we see 4 points like this, which are the tangent circle centers. There is no difference in terms of the geometric properties of the in-center and the ex-centers. They are just 4 points which are congruent in their properties. So we have 3 given points. We have the red circle, and we have this construction. So we have these 6. Maybe let's make these points blue. 6 blue points, which are like this, opposite to each other. So, but let me not draw all of it because it will complicate the picture. But what I mean is this. Hopefully, it can be seen. So we have 3 black points, the given points, given triangle. The red circle is the circumcircle. So from this we have 6 blue points, which are just the midpoints of AB. 2 midpoints for AB, 2 midpoints for BC, 2 midpoints for AC. So this gives me 3 diameters. These are the perpendicular bisectors of BC, AB. So this is the perpendicular bisector of AB, perpendicular bisector of AC, perpendicular bisector of BC. Now, these midpoints, when they are joined to the opposite vertices, they give me 4 lines. This is one green line, this is other green line, this is other green line, this is other green line. And they form 4 new points, 4 orange points. So on each green line, I have 2 orange points and exactly 1 blue and 1 black point. This is the configuration. Now, in this configuration, the story I told you is to start with so this is a configuration. I call these things configuration, like a shape. Yeah, configuration, setup, shape. But the story I told you is I started with the black triangle and then I constructed. The same configuration has the alternative story. You can start with the 4 orange points. They are not arbitrary points though, because any 2 orange points when you join and the other 2 orange points, they are perpendicular to each other. This is what is called an orthogonal system. So there are perpendicular angles here. So this green line and the opposite green line. So you can start with the configuration of the orange points and the green lines, what is called an orthic system or orthogonal system. Then from this, you immediately get the black points, and you get the red circle, and on the red circle you see the additional important 6 blue points. So with this narrative, the same configuration usually has a different name. There is the notion of a 9-point circle. Have you heard of this?
Yeah, I heard of it.
Yeah, 9-point circle of it's usually in literature I see it's defined for triangles, but the correct way to define it for orthogonal systems. And then I will hopefully tell you this. Yeah, so my intention was not to immediately start with lecturing. My intention was to solve the problem first and then start lecturing, but as the problem progressed, I digressed to the lecture a little bit. Hopefully I'll get to all of this. Inshallah, okay? I'll give you inshallah a lecture on triangle configurations. Maybe not today. Yeah, hopefully next week we can do this. If I give you a lecture on triangle configurations, you will see that the same configuration here is the configuration for the 9-point circle of an orthogonal system, and it's also the configuration for the tangent point circles, tangent point centers. So yeah, tangent circle centers, in center and eccentric, tangent circle centers of a triangle, angle bisectors of a triangle. This is one fundamental triangle configuration. So here, when you see therefore the angle bisector and the perpendicular bisector, their intersection is this point, which is a midpoint of the arc on the circumcircle. This is quite important. So this M is this one. So what have we proven? Going back to the original problem, what have we proven? That M is cyclic with ACD. So conclusion, MACD cyclic, concyclic. This is a circle in the original problem. So by symmetry, we have what? The first finding. So finding 1 is MACD, and what else? If we know something for M, we know the same thing for N. Who can tell me? Let's see. So has everyone understood the proof that MACD is cyclic? Or have you missed something? Or let me even ask you straightforwardly. Did you find in the exam? Did you find this in the exam?
I had a different approach.
Did you solve the problem at the end?
No, eventually no, but I think I was really close.
Okay, we can study, but I believe in this problem there is in order to solve you have to discover this as the first step. In any marking scheme, this would be part of it. And okay, you missed a part of the original part of the lecture, but it is recorded, so you can watch later on. But so far we have done the proof that MACD is cyclic, and it sort of just happened immediately. Like we were just trying to understand, and it came. Are you satisfied with the proof? Honestly.
Yeah,
Yeah.
I'm satisfied.
Which means you understood the proof that MACD
because
is cyclic. What?
yeah, because we know that the intersection of the circle of ABC and the angle bisector of A is the midpoint of the arc BC,
Yeah.
and the midpoint of arc BC is obviously like equidistant from B and C, and so it's in the perpendicular bisector of BC,
Yeah.
and so it must be
Yeah. Yeah, exactly. So this is this point. So going back to the original problem, we know that M is on the circle ACD, and by symmetry N should be on the circle what?
BD
ABD.
Yeah. ABD, yeah, NABD. So we have these two nice cyclicity. So this is one concrete first step into the problem. For example, in the marking scheme, this would be maybe the first point, something like this. But then, really, usually marking schemes are harsh. They just give you 1 point for doing something really important, and then once you can get that point, you can usually solve the rest of the problem. This is why partial points are not very easy. So then we should progress. This allows us to do some angle chasing now. Okay. This is very important finding. Allows us to do some angle chasing, because ultimately our goal is AMIN cyclic. Finally, we have some circles which go through M. In the beginning, we didn't have any circles that go through M. So how can you do? So in order to prove AMIN is cyclic, if you want to prove this with angles, we need some angles at the vertices M and N, perhaps, and those or lines
Okay.
using.
We can prove, we can use MAD and MIB or MIN.
So which ones? MI?
MAI, MNI,
Yeah.
or
So
yeah.
now we can know MAI, right?
Yes, and the other is easy to obtain.
The other is easy to obtain.
Yeah.
So how is it easy? Let me see. Okay. See, if it is easy, then the problem is even easier than what I thought. But it would be great that you solved it yourselves. Let me try to show this. So this angle here is equal to this angle, which is half of the half of C, right? So how can we obtain this angle? In fact, we can obtain this angle because this angle is part of such configuration, right? We can obtain it. this angle, well, N and M are of the same kind. So here, this was the picture. So if we are talking about this angle, to show that it is the same, this angle is the angle between the green line and the blue line. So it is exactly this green line and the blue line, this angle. So we can go back to this configuration and try to understand this angle. If we can understand this angle, we can go back to here and write this angle. Okay, who will want to do this? How can we write this angle? As you said, it should not be difficult. Now I understand. The solution in my mind was even longer than this. So amazingly, some even shorter solution appeared. So I can just do this angle chasing easily. What is your suggestion to do it?
We can actually just do some
So
angles.
what is this angle equal to in terms of the triangle angles? Okay.
Yeah, 180. We can just do this a few times and we can get
Yeah, no, this
the
angle, this the angle between the blue line and the green line is equal to what? In terms of the triangle angles. If I call this alpha equals what I mean to say is in terms of internal angles A, B, C, because since this is a standard figure, the angles here must be determined in terms of the triangle angles A, B, C. For example, this is A over 2. This is A over 2, right? This is A over 2. So I'm using A also to refer to the angle. This is B, this is C. This is what I usually do, to use the same vertex name to refer to the angle as well. Does someone know the answer? Well, if you know, as I told you last time, you should speak more often so that we progress faster and we solve more problems, okay? You should not hesitate to speak. That's what increases
so
my speed.
we can just connect M and C. We have
Mhm.
BCM, which is A divided by 2. So we can just calculate AMC and the angle yeah, so we can get it.
So yeah, can you just tell me and let's get it.
I
We
can,
have to do it for the problem. So you are saying you are looking at the triangle AMC and doing it from there.
yeah. So this is 1 degrees. We can get this, and we can also get
I mean, writing might be taking you time if you are doing it with a mouse or with a touchpad. You can. It's
okay.
better you tell me. It's better you tell me and I write.
Okay, so okay. This
You don't have to
angle,
erase. That's fine. Yeah.
this angle is B plus C over 2.
Yeah. Okay. B plus C over 2. Yeah.
And the whole
So this
angle
bottom must be 9.
is like B plus C over 2 plus alpha equals
Okay. Alpha equals
B.
180 minus this B plus C over 2 plus A over 2 plus C plus A over 2. Right? And this is already 90. Well, in fact, we found this from 90. Well, in fact, you don't even have to use a triangle like this because once you have this, alpha C, and A over 2, and 90 degrees. Do you know these three angles, their sum is this? You don't have to complete this to a triangle and do. This is a shortcut. Okay, I can do it with this shortcut.
Oh, okay.
So in general, when you have a concave quadrilateral like this angle is the sum of the three angles. Why? Because this angle, when you add with the internal angle, it should be 360 degrees, and this one, what makes it complete to 360 degrees? The other three. So here I can look at this 90, and I don't have to worry about this, whether this is A over 2 or B plus C over 2. Sorry, I erased too much. I even raised the circle, right? Yeah, so I can just look at this alpha C and A over 2. So this is 90 minus C minus A over 2. But I am not satisfied because I want to write the formula which is symmetric in B and C. That would be better because in the shape B and C is symmetric.
I think that we can improve that A, M, and N and I are cyclic by a simpler way.
Yeah, we will. Well, we will do this there directly. We will use the result. So here I'm trying to use. I'm trying to get the general result, and I will use the general result there. So alpha is 90 minus C minus alpha A over 2. So 90 minus A over 2 is B plus C over 2 minus C. So this is B minus C over 2. See, this is, well, anti-symmetric, not symmetric, but anti-symmetric, because when you change the order of B and C, alpha also becomes minus alpha. This is why. So this is the rule. This alpha is just B minus C over 2. So therefore, if I come here, this red angle should be what minus what over 2? You think? This red angle is alpha here. This alpha. But this is from which triangle? So in the general case, this alpha is from the triangle ABC, and it is the difference of B and C over 2. So in this case, this alpha comes from which triangle?
ABD.
Yeah, ABD. So alpha equals what angle minus what angle over 2?
It's D minus A over 2.
What, sorry?
ADB minus
Yeah, ADB, yeah, ADB.
minus BAD over 2.
Yeah, exactly, BAD over 2. Now this we can write in terms of the triangle things. BAD is just A over 2. And ADB is?
It's 180 minus B minus A over 2.
Yeah. Yeah, you can do that. Or again, another shortcut is to write it directly from the triangle ADC as the sum of the other two angles. This is also something I suppose you know, right? The external angle is sum of the other internal angles. So A over 2 plus C is ADB, which is what equal to what you are saying. 180 minus A over 2 plus B. Doing it like this is faster, and this is just A over 2. We subtract and we divide by 2, so this is just C over 2, which is the same as this. So this finished.
Yeah, but I think we can do it in another way by considering the angles A and B and AMC. It will be similar.
Yeah, let's do it. Okay, this is solution 1. Solution 1. Solution 2. Step 1 is the same, right? And after this, step 2, you do another angle chasing.
Yeah.
With what angles? Tell me.
A and C, A and B and AMC.
A and B and AMC. Okay. A and B. So you should get A and B from this circle, A and B, which is ADB. Ah, okay. This is even faster. Ah, great. This is even better. A and B. Great. A and B is just equal to ADB. Okay, amazing. A and B is just equal to ADB. And AMC is equal to ADC. And their sum is, of course, 180. But this is a better one. Better. Yes. You see, in any case, the first step is the crucial step. After this, it is just angle chasing. But to get the first step, it is not angle chasing. It is configuration knowledge. But to really see this configuration, so even if you see this configuration, even if you have this configuration knowledge, how do you actually see it in the problem? When you face the problem, you start to see it when you start to think in the manner that I told you, that I tried to describe to you through this example. You take this as a task of analyzing the shape. And as Abdullah said, you first do a description of what is important and what is symmetric, such basic analysis of the shape. And then you focus on the important part, you extract the relevant subshape. And then you start to see the configuration. And once you get some crucial knowledge, it can really help you progress in the problem. So this is, I think any solution of the problem must first observe this, in my opinion. But when you have a different approach, so Edham, for example, you said you had a different approach. Did you still get some result? Like some things are cyclic with each other, etc., which can be connected to this?
I tried to prove that I had way more points. I added more points from mine, and I tried to prove them cyclic.
Yeah, but when you add more points, then you have to prove more things. Because it's like algebra. When you have two variables, two unknowns, you need two equations to solve them. When you have three unknowns, you need three equations. So everything, every point is like an unknown, and every sort of description of the point is like an every relation the point satisfies with respect to the other points is like an equation. And we are kind of doing equations. By the way, I again, this is a part of my geometry philosophy. I should maybe write this as well. This is actually one particular form of algebra. So this is in fact algebra with pictures. Geometry in general is algebra with pictures. This is even for beyond Olympiad geometry as well. Well, beyond Olympiad geometry, it's not maybe necessarily pictures. Well, in all of mathematics, you draw some sort of pictures because even in combinatorics, you draw graphs, for example. Pictures are really important in all of mathematics. But in geometry, uh, Okay, what characterizes geometry is not this, of course, but it is it's a certain kind of intuition, a certain kind of way of thinking is really what distinguishes geometry in research mathematics from the other fields, is its own characteristic way of thinking. But otherwise, it can be considered a form of algebra. One way of doing algebra, but because of its own, let's say, internal structures, it enables us to think in different ways. So I can be conservative and write at least this more generally. Actually, this is not general. Another thing. Geometry is a form of algebra. It's a certain kind of algebra. Okay. So this is a statement that I'm 100% behind. I support this statement. So everything that we are doing here is that, as I said, shapes consist of points, lines, circles, and their relations. And the relations are like equations, and we we start with some given relations, we deduce more relations from them. It's sort of, we are solving equation. We are taking two equations and adding them and doing something to obtain the equation. So this is what is sort of happening behind the machine. It's like when you're using a computer with a monitor and keyboard and mouse. You see everything, on the monitor you control with your mouse, but you know that there is, CPUs inside the machine that actually transmit the electric signals, and that's what is working behind. So when you're actually doing geometry solutions, basically somehow there is algebra working behind. One way of justifying this is to think about coordinates of points, for example. You can give two coordinates to every point. Do you know about the coordinate system? Anyone?
Yeah, I do.
So there's this way of well even in when we open the map, the navigation, we describe points by coordinates, right? On the surface of the Earth, for example, which meridian it is and which latitude, which longitude, which latitude. So on the plane, every point has two coordinates, and then for every line, similarly, you can have two numbers to describe it, which are the coefficients of some equation. And then intersections and everything, all the informations can be written as equations. But of course, it is, if you are naive, if you don't pay attention, it is very complicated to write those equations and try to solve it naively by algebra. But there are smart ways of doing that as well. So people also use such things in Olympiad geometry. People directly use, if they know how to do it, directly use algebra, directly use coordinates, sometimes coordinates, sometimes trigonometry algebra, but coordinate systems also, there are various kinds of coordinate systems. This is also useful knowledge. But what is done in geometry like this, which is called synthetic geometry, this is what we are doing here, synthetic geometry, is because you synthesize the things. You take the pieces and you merge them together. So there is, in Olympiad geometry, there is analytic geometry and there is synthetic geometry. Analytic solutions and synthetic solutions. Of course, the problems are the same. Same problems. But analytic solutions directly put the coordinates or do trigonometric calculations, and they do the calculations explicitly. But then you have to know how to calculate it. And in synthetic geometry, you need to know some basic pieces, and you need to merge them together. but you know that behind the screen, actually algebra is working. When you do it with this spirit, you understand better. All right, so let's so today we can proceed like this. I can give you other problems and similarly discuss the solution like that. And then inshallah next week I can give you some dedicated lecture on for example triangle configurations, and another dedicated lecture on circle configurations. So today let's just continue like this to set the basis. So I'll find problems from my booklet. Uh, let's open a new page. So there's a circle, there's a circle. Okay. Points A, B on the circle. So let me points A, B like this. And there is point T on the line AB. AT, the length AT is equal to the radius. It is given like that. The point T is given such that AT is equal to the radius. Then the perpendicular bisector of BT intersects the circle with at M and N. And the line MT intersects the circle at S. So show that NTS and NTS is equilateral triangle. Okay, you should start thinking about this. Okay, let's get started to think. What are the things you have thought about? And then I will get you started to think. So any approach?
Maybe the intersection of T and the center of the circle is the midpoint of S and N.
Intersection of what?
Intersection of the line T O, which is the center of the circle, and S N is the midpoint of arc S N.
I mean, is this a guess, just a guess, or do you have any justification?
I'm trying to prove it completely, yeah.
But no, I mean, if you have not observed it from something, then it might be a wild guess and it might be wrong, possibly. And in geometry, usually we don't have such, like, it's not like you don't get insights like in combinatorics and I mean, you do get insights, of course, but it's not that almost somehow you first sense and you prove later. Usually it becomes proof usually comes by itself. When you get the fact, it comes with the proof, typically in geometry. Somehow in combinatorics you observe the fact and you're convinced and then you need to find the proof. But in geometry, usually when you get the fact, it comes with the proof. When you get the fact right. So this is why I always when I do geometry training, when I ask the students what they have done, I always emphasize, what observation. By observation, I mean what it's like. As I said, it's a kind of algebra with equations. Kind of what have you obtained as with proof, or what? And even before that, before obtaining anything with proof, as we saw in the previous problem, it's really just the right way to start thinking. So if we start thinking about the setup, so there is the circle and the 2 points. This is the basic setup. And on top of this, some unique configuration is made. So the point T is the first interesting point to be defined. Let's try to understand a little bit. I mean, not there's not much to understand because it's already on the line AB and it's defined by the distance. So let me ask you this interesting question. Is T uniquely defined? What defines T geometrically? To define a
Uh,
point, what?
it's a circle and a line.
Yeah.
A circle with center A and radius R and the line AB, and it's
Yeah.
inside the circle,
So
so it's not.
insideness is the unimportant information. Okay. So this adds to my geometry philosophy, but let me first so it will be part of my main philosophy for this Olympiad type of geometry. It is well, geometry in general is a certain kind of algebra, but as a so main philosophy for Olympiad geometry. Okay, let's say this is uh so what was I saying? Yeah, in this Olympiad geometry especially, there are well, as I said, I mean, as I explained to you just in our previous discussion, that geometry is a certain kind of algebra, and namely there are equations, equalities, and from the equalities you obtain equalities. The relations that we know in geometry, they are all of the major relations that we know are of the equality type. And there are things that are of the inequality type. So informations, any kind of information that is given about a shape, about a configuration. By information, I mean some relation between points, lines, and circles. We have to be conscious whether this is of the inequality type or whether it is the generic type, which is of the equality type. To understand this distinction. And let me try to tell you what this means by giving examples. So when you say that two lines are parallel, this is an equality. When you say that a line is tangent to a circle, this is an equality. A circle is tangent to a circle, this is an equality. Equality. All of these are equalities. Parallel lines are lines are parallel to each other. Lines are tangent to circles. Circles are tangent to each other. Points are collinear. Lines are concurrent. Points are concyclic. What other examples can you give? Four lines share a common tangent circle. All these kinds of relations are equalities. And then there are the other more obvious equalities like perpendicular bisector, because bisector clearly the sides are equal, and angle bisector, or in general some angle is equal to some angle, some triangle is isosceles, some triangle is equilateral. All of these are equality kind of relations in geometry. What is an inequality type relation? That to say that a point is in the interior of a circle, interior of a triangle. A point is in the interior of a circle, not outside but inside, or it is outside. It's the opposite inequality. To talk about inside and outside, or to talk about the left side, about the right side and the left side of some line, or talk about inside of the segment or in the extension of the segment. These are the inequality type informations, which are rare. So in the problem narrative, problem stories, when they describe the story, they have both kinds of information together. To describe the shape, they usually have equality type informations, but and also inequality type informations. But the conclusion statement is almost always just an equality statement. Prove that some things are concurrent, some three lines are concurrent. Prove that some 4 points are concyclic. Like in the previous problem, prove that they are concyclic. Prove that A and ion are concyclic. And in the other, in the current problem that we are working, prove that the triangle is equilateral. And this suggests something which is very true, generically true, like 99% true, that equalities follow only from equalities. Inequality information that is given in the problem doesn't matter. 99% of the cases, it doesn't matter at all. And this is a very radical statement, but it is, by experience, by long experience, this is correct. So some questions naturally occur here. So why do they give those information? Just to make sure that everyone draws the same picture. There is no other reason they give that extra inequality information. Because if they don't give it, you might have different pictures. Even internal bisector and external bisector, there is no difference between them. It's just one of them goes through the inside, the other one goes through outside. This is also inequality type information. What is really important is that it is bisector of the angle. And if you just work with any bisector, they have the same properties. For example, in this problem, instead of the in-center, if you did the problem with the x-centers, you would have the same result. And you would basically have the same proof. You would just have to adapt the proof. Okay? Let's do this, in fact. This is very very useful exercise. These are the things that get you look at the Olympiad geometry from on top of a hill, from above. So you see everything together. That gives you a powerful position. Okay. The things that these are the mottos that I have extracted from years of experience. So it kind of speeds up your learning. So let me add this to here. Generally, equality type results follow purely from equality type results, equality type information. So there is equality type results, and they follow purely from equality type information. In the problems, well, they give inequality type information only to fix the picture. Which is what I'm saying here. The same shape, same configuration, same abstract object can have different pictures. And it's a good thing to be able to draw different pictures, because with different pictures you understand the same thing differently. And it adds to your understanding. But when the same shape has lots of different pictures, if one student draws one picture, if another student draws another picture, it becomes hard to evaluate it for the coordinators. So they just want to fix the picture. And since most people don't know this, it's just the custom. It's just what they are used to. This is why they need to give the inequality type information. But at the end, when you solve the problem, you don't use it, in fact. It's just in the picture and it's in your mind. But the facts, like what implies what information you took, what information you used to derive the other information, and how did you solve the problem, the inequality type information is not present. Generally, 99% of the cases. So what is like 1% exception? I would say it is sometimes actually you have say intersection of a circle with a line, but this somehow the circle and the line are themselves defined in terms of the other points. So there is already some basic shape, and on this basic shape, some line is defined, some circle is defined in some way, and the intersections are naturally two different points with two different properties, and they just want to distinguish one of them from the other. Somehow they can distinguish with saying that this is inside, whereas what is important there is it is not that it is inside, but it's already a point with a different property, and it just happens to be inside. This is how it is distinguished. Sometimes if it is like that, implicitly inequality type information might contain equality type information in some sophisticated cases. Only in those cases it can matter. Otherwise, generically speaking, there is no difference between internal bisector and external bisector. In a generic triangle, absolutely. And this is, by the way, related to, for example, the case of the internal bisector and the external bisector. The case of the four orange points here. There is no difference in their properties. It doesn't matter that this is inside and the others are outside. They have the same properties geometrically, the same equality type properties. And this is related to Galois theory. Okay. This is a consequence of Galois theory. In abstract algebra. So let me write more. What is equality type? What is inequality type? Equality type, inequality type. Well, inequality type is really inside-outside thing, okay? Interior, exterior. For example, two circles are tangent, but tangent from the outside or tangent from inside. Inside, outside. Yeah, extension type of this kind of things. But equality type is, of course, all the things that we know, like parallel, tangent, collinear. So when 3 points are collinear, for example, A, B, C, which order are they? Are they ordered like A, B, C or A, C, B? Which one is in the middle of the other two? This is an inequality type thing. But to say that they are collinear, this is equality type thing. Concyclic. What else? Perpendicular. Like isosceles. Many things like that. So in particular, internal and external angle bisectors. Internal and external angle bisectors have the same properties. Okay, they always have the same properties. Whatever theorem you have for one of them, you have an analogous theorem for the other. So let's do this. Let's apply this philosophy to this problem. In this problem, the incenter is taken, and with the triangle ABC and the incenter is taken, and then the shape is constructed. Instead of the incenter, if some other excenter were taken, and M and N were defined according to this, we would still have A, M, I, N concyclic. So do you see this kind of a radical thing? So what do you think about this? When I say radical, I mean it's not obvious. It's not, it might be surprising when you hear it for the first time. But then when you do it, when you see it a couple of times, you see, yes, definitely this is the case. So this is something that I have myself extracted after long years of experience. And this really, these are the piece of, say, perspective, the way of looking at geometry that enhances broadens your perspective and allows you to progress in geometry fast. Okay. Let's take this and let's take I to be this one. Which one? Let's say I is this one. Okay. This bisector. So okay, let's draw it better. ABC. I can take this angle bisector in the problem. I have actually four choices, right? I can take this angle bisector, and on this I can take this eye or this eye. Or even in the internal bisector, I can take this eye or this eye. So there are four centers. So let me just take this one. Which is on so this is point D, right? This is point I. That's right. So green line will be what? It's the same. Verbally, it's the same. Because the narrative doesn't see the picture. The picture doesn't see the narrative. So in the narrative it says it's the perpendicular bisector of AD. So I should just do the same thing, perpendicular bisector of AD. Okay. So this intersects BI and CI at the points N and M. This is point N. And this will be point M here. It might look like a totally different picture, but it is the picture of the same shape. So in this one, the question is to prove that this, and this are concyclic. And in fact, it is true. We can do the same proof. MACD cyclic. Let's see. Yeah, this MACD cyclic. How did we find MACD cyclic? We found it from the triangle ACD. Still, we can find it from the triangle ACD. How? Any idea? Can someone tell me? I just want you to speak to make sure you are also following. When you look at this triangle ACD, what is M? M with respect to triangle ACD. M is what? Just say it, guys. Whoever wants to speak immediately should speak.
Yeah, it's like the point that was diametrically opposite to in the previous
Yeah,
point.
but it is it's still M,
Previous case.
right? Yeah, it's still M. So this is still some
Yeah.
angle bisector. It's the external angle bisector, but it doesn't matter. So external angle bisector and uh, perpendicular bisector. In this shape,
Yeah.
in this full configuration, we have all of them. In this full configuration, we have external bisectors also intersecting with perpendicular bisector on the circle. Because this is the midpoint of the big arc. So this is still what it is. So intersection of perpendicular bisector and intersection of the angle bisector. It has to be on the circle. Similarly, for N we look at the ABD, triangle ABD. And for this is also external bisector. Internal in ABC, but external in ABD. For triangle ABD, this is external bisector and again perpendicular bisector. So this is also on the circle. So AB and D and ACM D, and from this we can do the same angle chasing. We can look at angle A and B. A and B, it's gonna be equal to ADB, and ADB is just ADC. It is going to be, so let me write in this case proof 1 is the same. When we do the proof, step 1 is the same, and in step 2 it will be essentially the same, analogous. A and B equals ADB, yeah. And we are looking at we want to look at AMC. AMC equals ADC. This time we don't want to show that their sum is 180, because this time A and B and AMC are like this. So we just want to show that they are equal. And in fact, they are equal this time. ADB and ADC.
What if we consider like the other permutations of the angle bisectors of A, B, and C? Will we have the same thing?
By other permutations, what do you mean? Yeah, there are 4 permutations, right?
For the-
4 in my opinion. Which other permutations do you mean?
Aren't they like 8? Well,
So you are saying 2 times 2 times 2. Okay, yeah, there are two for each vertex, but of those 8 triples, 4 of them give you concurrent lines, 4 of them don't give you concurrent lines. So that's a geometrically completely different picture, a completely different setup. So if you take the internal bisector here, external bisector here, and internal bisector from this one, for example, then there will not be a point I in the problem. Because here you want a point I, and you want to have blue lines BI, CI, and you want the point D on the line AI. So this is why half of them are not valid. So in this picture, yeah, at every vertex there are 2 green lines. So you can say 2 times 2 times 2, 8. I can make 8 triples, but each of these 4 orange points correspond to a triple of green lines. And then there are the triples like this. This green, this green, this green. Not concurrent. Those are not the triples that we consider. Is this satisfactory?
yeah.
Yeah, so geometrically it's not comparable. It's not the same thing. Yeah. I don't know what happened. My writing experience is really bad now. Tablet doesn't write well. Okay. Yeah. So this is a really important part of general geometry philosophy. So in this problem that we are working on right now, T is a point whose distance to A is like the radius. So T is on the point whose center is A. So T is on the circle whose center is A and which has the same size as this circle, same radius. And that circle will intersect the line AB. So T could be here, inside or outside. Of course, in the problem wording, they will tell you it is inside. They will not want you to draw it outside. But if you draw it outside, it is the same. And observing these things before solving the problem is usually important. Uh, Alternative pictures. For example, AB could also be a short segment, so T goes outside from both sides. That's also possible. Well, in this case, you can have, for example, BT perpendicular bisector BT like this. Now, sometimes in different pictures, we see different things. We see ideas differently, and somehow some idea comes to our mind in some picture, and we prove it. And then once we find the proof, we can find the proof in all cases, of course. We can easily adapt the proof. And sometimes some idea comes to our mind which is not correct. And when we draw different pictures, it becomes obvious that it cannot be correct. Because if it looks like correct in all the different pictures, then it might be correct. But sometimes it's just the picture is deceiving. If you are looking at one picture, it might be deceiving. Okay. So here, what is S? Here, this is S. But of course, this 80, I didn't draw well, right? 80, I drew it too big in this picture. So this is why NTS doesn't look like equilateral. Maybe I should draw the more reasonably. I must have a big circle and okay, this 80. So yeah, this is approximately like the radius. So it could also be out from this side. Right. 80 looks like the radius almost. Yeah, I guess. Anyway, when we prove it, we will see. But for example, what you said, Adham, was TO. What you said about TO doesn't seem to be correct in this picture. So it cannot be correct, actually. By the way, you said O. Wait, what did you say exactly? You said center O and the midpoint of this?
I said that the intersection of TO and the circle is the midpoint of the arc SN.
But this cannot be. Look, if this is the midpoint, and if this is O, if you join this is already the perpendicular bisector of S. Okay, it has to be correct.
It
Okay, now
has to be. I found
has
that N is the midpoint
okay.
of
Now
B
I
and
understand
S.
what you mean. Okay, it has to be correct. All right. All right. So it has to be correct, but uh, because it's if Ts equals Tn, it has to be correct. Yes, which is what we need to prove. However, I'm not sure if this is easy to prove because you are adding points. So you are adding 2 points. You are adding the center and you are adding the midpoint of Sn. When you add points, you have to be really careful. Do these points really bring information to you? You cannot just add points for free. It comes at a cost. It comes at a cost. The cost is sometimes justified when it brings benefits. So when a point comes with many relations, then we add it. But when it just comes with its own properties, it may not be useful. A center, if it's just a center, then what do we know about it? But if we know that the center is, on some line, on some circle, it comes with many properties, then it becomes justifiable to add those points. Another good thing is to watch out for the symmetries. For example, in this problem, which points are symmetric?
BT and BT.
No, I don't mean symmetric in that sense, like symmetric in the permutation sense. This is what I mean. What you said is geometric reflection symmetry. Yeah, that's another. I meant permutations. Like when you say a triangle ABC, it doesn't matter which point is A, which point is B, which point is C, and you can change the names. Changing the names is a permutation. So this is also called. So for example, here in this lemma, points B and C are symmetric in the permutation sense. If this is B, this is C, you still have the same lemma. Uh, so they must also have the same properties, naturally. So usually, I mean, the points that are defined with the same properties must be like that. So in this problem, when it first starts, it starts with points A and B. They look like symmetric, but then something A is given a special role in the definition of T. T is defined with respect to A. So now they don't have the same role anymore. A and B are distinct points, and T is a totally different point. Then which points are defined? M and N. And you can notice, what can you notice?
They are symmetric.
Yeah, so they are both defined as the same thing. There is one line and one circle, the two intersections, they are called MN. So if this was called M, then S would be here. Then we would talk about this triangle as NTS. So this should also be collateral. We should watch out for this. Maybe somehow they can both be useful at the same time. Sometimes thinking about the two symmetric things at the same time becomes useful. So, yeah, therefore, Edham, I suggest not to focus on that idea because it's not clear how to prove. Facts should come with their proofs. We should just start from the given things. How can we prove? So, from this shape with angle chasing, etc., what can we prove? Let's see everything that we can prove. But let's understand the layers here. So there is the point T, and after the point T, there is point M and N, and somehow point S is defined. We want to prove something about S. Okay, before. So these are the layers, the basic figure, and on top of this, there is point T. So as I said, this is why the previous problem was easy. There was just one layer. You just needed to understand point M and N in the previous problem, and they were symmetric. You just needed to understand one thing. So here you need to understand at the end point S. But point S comes from points MN and point T. And M and N themselves come from T. So first there is T. At the basic level, at zero level, there is the basic figure, but then point T is defined, then MN are defined, then S is defined. And we can try to solve the problem at the different layers differently by so in our analysis, first basic figure from this point T is defined, from this points M and N are defined, from this points S are defined. So how can you start thinking about the problem? You can try to get properties of T maybe, but it's already obvious. So you can try to get properties of M and N in relation to T. Maybe this is something you can try to focus on.
You
Or
can show that an S is equal to NT
NS
easily.
equals NT. You showed it?
Yeah, easily.
Great. But when did you show it? Just right now or before?
No, before.
Oh, okay. Okay, so I'll take it. Listen to it in a minute. So this is something you can try to do. Another thing is to understand point S, to see well, in relation to all these points, especially in relation to the triangle. Since we want to prove that it is an equilateral triangle, what can be done? It could be about angles. For example, this angle looks promising. We can try to prove that this angle is 60. Or we can look at some sides and Sn is a chord, so it seems to be better understandable. Then should we compare Sn to St or Nt? Which one can be more easily proven? Let's be smart. So this is the way to think. One way to approach the equilateral triangle is to get something about the angles, or another way to get something about equality of the segments. So we need to get something with S for sure, but Sn is somehow better segment than St because Sn is a chord, so I can do something with it. And instead of St, I would do something with Nt because when I work with Nt, I don't need to worry about S. I can also do something with it. Now, what can you do with Nt? So Ethem already knows the answer, but maybe I'm trying to get you to think about it. If you try to say something about the segment Nt, what do you see? Thinking about the property of n as being on the perpendicular bisector of this. Because this is the definition of n. N is on the perpendicular bisector of BT. And what's the meaning of perpendicular bisector?
NT equal NB.
Yeah, NT equals NB. You see, this is great. NT is already moved to a chord. Now maybe we can prove that this is equal to NS.
We can use the cyclic quadrilateral NSMB, and since we know that SMN is equal to NMB, it follows that NBS is equal to NSB.
Exactly. So now these are both chords. To prove that the chords are equal, you need to look at the angles. So you will look at the angle. So this is so you need to look at the arcs, the angles which look at it. So which vertex can I choose on the circle that looks at this? Vertex A, no, it doesn't look. I will need to draw two more sides. It's not good. But vertex M is good. So it's already connected. So there is this line, and I can look at this line to compare these angles, and they are equal indeed because of this isosceles triangle. Since these angles are equal, this is also equal to this. Equal angles look at equal chords. So this showed us that NT equals NS. And so far we have done everything at this level. We have not even used the definition of T. This is very important observation. So for any point T on this line, we proved this. This equality. So the remaining equality cannot be correct for any point. Do you see? For any arbitrary point on the line AB, NT is always equal to NS. So the triangle NTS is always isosceles triangle with the top point at N. But somehow when AT equals the radius, then this side length is also equal. At that time, the angles become 60 when AT equals the radius. So this is what we should see. So similarly, on this side, you can get this equality easily. Yeah, this equality. But to get this one, let's call this one S prime. Okay. Yeah. This is point T. So first, let's write our first observation. Angle SMN equals angle Uh, well, this is the same thing as angle TMN. And by symmetry, this is angle NMB. So from the circle, this shows that SN equals NB from the circle. This is from symmetry. Yeah, so now Ethem, yeah, this is symmetry in the sense that you are saying reflection symmetry. So let me write. This is from the circle. This is reflection symmetry. And from the same reflection symmetry, we get Tn equals Nb. So this gives us Sn equals Tn. This is true for any point T on the line AB. Okay. Okay, it's already been long, so let's try to get the final idea to prove. Maybe we should see some 60 degrees somewhere or get something about this segment. 60 degrees, seeing 60 degrees might be reasonable because there's a circle. We can maybe find something, but how can we get 60 degrees? Well, somehow AT equals radius should be used. So probably some equilateral triangle with the radius, or in other words, what happens is that when you have a chord which is equal to the radius, then the central angle there is 60. When you have a chord. So maybe we can find a chord which is equal to AT. By the same way, we can find a chord which is equal to AT, and then from there we can find 60 degrees and we can carry it over on the circle. This looks like the most doable project instead of adding other points.
We have AC equal AT.
AS equals AT.
AS, I mean.
Yeah. Yeah. How did you prove?
Because of the similarity, AST is similar to TMB.
Wait, why? AST equals TMB. Yeah. That's right. That's right. Good. So yeah, that similarity, yeah, is just can be found by angle chasing, right? So you can simply say this, since these angles are equal, this angle and this angle, and this angle is the same as this angle, but this one is also here. So TMB is isosceles, TAS must be isosceles. Always these two angles are these are already at the same vertex, and these angles are equal by the circle. In general, this would be similar to this. And by similarity, you can say this isosceles and this isosceles, or by these angles, you can say these are equal. So very good. So AT is equal to this. So we should use that AS is a chord length. So AS is seen by 60 degrees from the center, and it is seen by 30 degrees from vertices. So this is second information. Let's prove it. So AST, so what Kerem said is angle AST equals angle TBM, which is the same as MTB, which is just STA. So it is AS equals 80. This is also true for any point on any T on AB. This is also true. But after this, we can now say AT equals radius. Maybe we can use it here. So using that AS equals radius, we should be able to see some 30 degrees, 60 degrees stuff somewhere. So we know this is equal, and so let's show it on the picture. We know this is equal.
Oh, I think I got it.
Yeah,
So
tell us.
we can extend a diameter from us, and we'll have to some point on the circle. Let's just give it some name. So we have 90 degrees and sine and sine 1/2. So we have 30
Yeah, well, you
degrees,
are
and this
basically
is
you are telling me you are justifying the 30 degrees of chord, right? So this is a general fact.
yeah, and
So
that should be
maybe
equal to
so let me I'll show it here as a general fact.
yes, and then we can just do a and us equals 30 degrees, and since both of these triangles are
So for this general fact, Karim, it's better to express them in a different setup, in a general setup. Coordinators
as
also
a
understand it much better when you write your solutions in IMO as well. So when you want to say that this angle is uh, any vertex sees this at 30 degrees because this is equal to the radius, this is a general fact. It's not about this problem. So it's better to express it separately. So the general fact, if AB is equal to radius, if AB equals R, then any point sees this at any point Q sees this at 30 degrees, right? And you wanted to prove this. The way you proved it is you drew the diameter here. You drew this one, so this is the diameter. You said this is 90 degrees, and this is so R to R 90 degrees, so this should be 30. Right? You said it like this.
yes,
Yeah. But someone else could also say it like this. Well, let me just look at this equilateral triangle, R, R, and this is 60. If the central angle is 60, this is 30 automatically.
yeah.
So, but in any case, this is a general fact. Okay? So we should use it here. So how do we use it here?
We just extend a line from A to M.
Yeah.
Uh,
This is the important
and
part.
it should be and
This
since
30.
AST and ST are both isosceles, it should bisect both angel SAT and angle SAT and angle SNT.
Yeah. Because this is a deltoid. And this should be perpendicular and it should bisect this one also. It should be symmetric. So when you have two isosceles triangles on the same base, This is a deltoid. So from this, you have a deltoid. AS equals AT, SN equals NT. Right, SN equals NT, AS equals AT. So when you draw AN, this is symmetric. You have equal angles, an equal thing, because since A is at the same distance to SNT, it must be on the perpendicular bisector. And N is also at the same distance, so it must be on the perpendicular bisector. So this must be the perpendicular bisector of this. And 30 degrees comes from this. So it is 60, yeah. So AN is the bisector. Well, bisector, also altitude and everything, because it's in. So this is the axis of the isosceles triangle. AN is the bisector of vertex S. Sorry, vertex N. And in triangle SNT. This is, by the way, still valid for any point T. This is still valid. It's just this 30 degrees comes because of that is equal to radius. Finally, since AS is radius, AS equals AT is radius, ANS is 30. And that finishes. It's just, this is used only at the last step to get this. You see, this is how geometry problems are really solved. We go like this. We proceed in this way and we solve. And the same solution can be done on this picture. All right. So we call today for today. I'm pausing the recording.